right, let's go on an architectural tour. But we're not looking at buildings today. No, we're going way, way smaller, diving deep inside the stuff all around us to check out the hidden atomic architecture of solids. And trust me, what we're about to find is going to completely change how you see the world.
So let's kick things off with a real head-scratcher. How is it possible that a single element, pure carbon, can create both the hardest substance we know of and the super soft, flaky stuff you find in your pencil? The secret isn't what they're made of. It's all about the blueprint.
So, to get to the bottom of this, we first have to understand that every solid out there is built from one of two master plans. One is just a masterpiece of perfect order, and the other, well, it's a little more on the chaotic side.
On one side, you've got your crystalline solids. The best way to think about these is like a perfectly built brick wall. Every single atom has its own precise, repeating spot. This incredible order is why they have such a sharp, specific melting point. Then, on the other side, you have amorphous solids, think glass or plastic. These are more like a jumbled pile of bricks. There's no long-range order at all, so they just get softer and softer and melt over a whole range of temperatures. And you can literally see this difference right here. Look at the beautiful, sharp, perfect edges on that quartz crystal. That's a direct result of its perfect internal order. Now compare that to the blobby, irregular shape of an amorphous solid. One's built from a precise blueprint. The other is just a jumble.
Okay, so let's leave the chaos behind and jump into the orderly world of crystals. For the rest of this explainer, we're going to focus just on these crystalline solids, because their amazing order follows one of 4 distinct architectural blueprints, and it's all defined by how their atoms are, glued together.
Think of this table as our cheat sheet for crystal blueprints. Find that covalent network column, and there it is, diamond. Its atoms are locked together by these incredibly strong covalent bonds, and that's what makes it so unbelievably hard. Now look over at molecular solids, like ice. The molecules there are just held together by much weaker forces. That's why it's so much softer. And then you get to metals, with this fascinating sea of electrons that holds the whole thing together. You see, the type of bond doesn't just connect the atoms, it gives the material its entire personality.
Okay, so if a crystal is a giant brick wall, what's the actual brick? Well, in chemistry, we call that the unit cell. This is the absolute smallest repeating pattern. It's the fundamental blueprint that gets copied over and over and over in 3 dimensions to build the entire crystal. If you can understand this one little block, you can understand the whole structure. All right, so we've got our building blocks. The next big architectural question is, how do you stack them? Nature is all about being efficient. So how are these atomic bricks, or maybe it's easier to think of them as oranges, packed together?
To measure this, scientists use something called the coordination number. It's actually really simple. You just count how many neighbors are directly touching any single atom. The higher that coordination number is, the more crowded the atomic neighborhood is, and the more tightly packed the whole structure is.
This chart really shows you what that looks like in practice. Take a look at the least efficient arrangement, the simple cubic. Only 52.4% of the space is actually filled by atoms. I mean, that is a lot of empty space, but as you move to the more complex arrangements like body-centered and face-centered cubic, boom, the packing efficiency jumps way, way up. And here it is, the absolute limit, 74%. You simply cannot pack identical spheres any tighter than this. It's a mathematical constant, a universal speed limit for packing, and it's the structure that a ton of metals like copper and gold naturally use to be as dense and stable as possible. So we've been talking this whole time about these perfect, repeating, beautiful structures. But here's a fascinating twist. In the real world, no crystal is perfect. They all have flaws, or what we call defects. And weirdly enough, it's often these tiny little imperfections that make a material so useful.
The simplest defects are called point defects. A vacancy defect is exactly what it sounds like. An atom is just missing. It didn't show up for work, leaving an empty spot, just like a missing brick in our wall. A self-interstitial defect is the opposite problem. You've got an extra atom that's been squeezed into a place where it just doesn't belong, creating this little bit of atomic level crowding.
Now, in ionic solids, like your table salt, you get this special kind of vacancy called a Schottky defect. See, to keep the electrical charge balanced, you can't just have one positive particle go missing, so they have to go missing in pairs, one positive and one negative. The crystal stays perfectly neutral, but because some atoms are gone, its overall density actually drops. It's a perfectly balanced imperfection.
So we have the bonds, we have the packing, and we even have these little, almost intentional defects. But how does all this atomic architecture actually translate into the real world? Well, it turns out those imperfections aren't just quirks. They are features we can control to create the technology that powers our entire lives, electronics. To get this, we need to talk about something called band theory. It sounds complicated, but here's the gist. When you pack all those atoms so tightly together in a crystal, their individual energy levels kind of merge and smear out into these huge energy bands. And the key to absolutely everything is the space or the gap between these bands.
Let's break it down real simple. You've got the valence band, which is totally full of electrons, just hanging out. Above it, there's this empty level called the conduction band. Now, for electricity to flow, an electron has to make the jump from the full valence band up to the empty conduction band. And the band gap? That's just the size of that jump.
So here's the crucial part. In a metal, there is no gap. The bands actually overlap, so electrons can just move around freely. That's why copper is such a great conductor. In an insulator, like rubber, that gap is massive. Electrons are totally stuck, they can't make the jump. But, and this is the big one, in a semiconductor like silicon, the gap is small and, most importantly, it's controllable. We can give electrons just a little push of energy to make them jump. This ability to turn conductivity on and off is the foundation of every single computer chip on the planet.
And so we come full circle. Diamond and graphite, same atoms, totally different blueprints. We've seen that everything from the type of chemical bond to how efficiently you pack the atoms matters. But maybe the biggest takeaway is that even imperfections, those tiny little flaws, when we control them, are what enable our entire modern world. It just proves that the tiniest changes in atomic architecture create these enormous differences all around us. It really makes you wonder, now that we understand the blueprints, what are we going to build next?